So let us begin with lecture 3 of electric potential and capacitance. So we will begin with this lecture with some numericals. So we are dealing with the first one. A charge of 8 millicoulomb is fixed at the origin. Calculate the work done in taking a small charge of minus 2 into 10 to the power minus 9 coulomb from a point P 0,0,3 centimeter to a point Q 0,4 centimeter, 0 via a point R 0,6,9 centimeter. So if we consider this problem, so the work done due to the electrostatic field is independent of the position it attained while going from point P to Q. Since it is an example of a conservative force, so point R is of no importance in this problem. So let us begin like this. So we say that the charge which is fixed at the origin, we are calling this as Q1, and it is equal to 8 millicoulomb, that is 8 into 10 to the power of minus 3 coulomb. And the charge which is being taken from point P to Q is referred as Q2, which is equal to minus 2 into 10 to the power minus 9 coulomb. So we consider the initial position as point P, which is 0,0,3, and the separation between them can be written as R1, which is equal to 3 by 100 meter. And the another point is point Q, which is 0,4,0, and this time the separation is regarded as R2, which is equal to 4 by 100 meter. So considering this, we write the initial potential energy which the system is having, which is equal to K Q1 Q2 upon R1. Now since over here the forces is attractive in nature, so we say that the potential energy value will be negative, and we write it as minus 9 into 10 to the power 9 into 8 into 10 to the power minus 3 into 2 into 10 to the power minus 9 upon R, which is equal to 0.03. So from here we attain a value equal to minus 4.8 joule. So if we calculate the final potential energy for this system, we again use K Q1 Q2, this time R2. So the value is minus 9 into 10 to the power 9 into 8 into 10 to the power minus 3 into 2 into 10 to the power minus 9. The separation is 0.04, and the value of energy is equal to minus 3.6 joule. So if we calculate the value of work done, so we say therefore work done is equal to U final minus U initial. So it is equal to minus 3.6 plus 4.8, which is equal to 1.2 joule. So 1.2 joule of work is done in this particular problem. Let us deal with the another problem. So the problem is stating, in a hydrogen atom, the electron and proton are bound at a distance of about 0.53 angstrom. The question is, estimate the potential energy of the system in electron volt, taking the zero of the potential energy at infinite separation of the electron and proton. The next one is, what is the minimum work required to free the electron, given that its kinetic energy in the orbit is half the magnitude of potential energy obtained in part A. The next one is, what are the answers to A and B above if the zero of the potential energy is taken at 1.06 angstrom separation. So if we consider this problem, so we say that in the first part, the problem is saying that the separation between the two charge is equal to 0.53 angstrom, and the two charges are, so we can write it in 0.53 into 10 to the power minus 10 meter, and the two charges are having the magnitude which is equal to electronic charge 1.6 10 to the power minus 19 coulomb. So the electron will be having a negative charge while the proton will be positively charged. So if I write the potential energy for this system, So it is equal to K Q1 Q2 upon R. And since the force is attractive in nature, the potential energy will be negative. So we will write it as minus 9 into 10 to the power 9 Q1 Q2, that is 1.6 10 to the power minus 19 whole square, and the separation, which is equal to 0.53 into 10 to the power minus 10 meter. So the value will be obtained in joule, and it is coming equal to minus 43.5 into 10 to the power minus 19 joule. So if we convert it into electron volt, so we say that 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule, and hence we can say that the value of energy can be written as minus 43.5 into 10 to the power minus 19 divide by 1.6 into 10 to the power minus 19, and the value will be in electron volt. So it is equal to minus 27.2 electron volt. Now the value of potential energy, so this was part A. So if we come to B part, the value of kinetic energy is equal to half the magnitude of potential energy. And since the kinetic energy is positive, so we take the value equal to 27.22 divided by 2, which is equal to plus 13.6 electron volt. So the value of kinetic energy is plus 13.6 electron volt. Now in the third part, the question is saying that the zero of the potential energy mark is taken at 1.06 angstrom. So how is it going to affect our answers? So the value of kinetic energy is not going to be affected because it is equal to half mv square, and since there is no relative velocity involved, so we say that the kinetic energy is remaining unaltered, which is equal to 13.6 electron volt. Now we say that the potential energy of the system is written as, so whenever we define potential energy of a system, we define it with respect to infinity, that is we write it as potential at infinity minus potential at separation r. So we have always done it in this way. So when we do it in this way, so now we are saying that the new potential is at r, which is equal to 1.06 angstrom, is taken as 0, is the point of u equals 0, and hence the first thing that we do is we calculate potential energy at this point. So it is equal to 9 into 10 to the power 9 q1 q2, that is 1.6 into 10 to the power minus 19 whole square, and the separation, which is equal to 1.06 into 10 to the power minus 10 meter, and the value is obtained as 21.73 into 10 to the power minus 19 joule, which we convert it into electron volt as 13.58 electron volt. So now the new value of potential energy is equal to 13.58 minus 27.2. So the value is equal to minus 13.6 electron volt in this new configuration. So let us deal with the next problem. So the next problem is stating two charges minus q and plus q are located at points 0, 0, minus a and 0, 0, a respectively. The first problem is, what is the electrostatic potential at the point 0, 0, z and x, y, 0. The next one is, obtain the dependence of the potential on the distance r of a point from the origin where r by a is greater than 1. And the last part, how much work is done in moving a small test charge from the point 5, 0, 0 to minus 7, 0, 0 along the x-axis. And does the answer change if the path of the test charge between the same points is not along the x-axis? So if we consider this problem, so let us begin it in this way. So the first thing that we are doing is we are doing the coordinate axis. So we are considering this axis as the z axis, and the xy plane is something like this. So this is the xy plane, and this is the z axis, and this one is the treated as negative z axis. So the position of the two charges is something like this, that the plus q charge is at a distance a on the z axis, and the minus q charge is somewhere here at a distance a on the negative z axis. So if we write potential on the z axis, so now the first thing is clear, that the x and y axis in this problem is along the equatorial plane, and hence the value of potential on x and y plane is 0. So the value of potential on x and y plane is 0, and at a point z on the z axis, which is the axial plane for the dipole, we say that the potential is given by the potential due to positive charge, that is kq upon z minus a, and potential due to negative charge, which will be minus kq upon z plus a. So any point z on the z axis, if I show you like this, that if we consider z somewhere here, so the separation from the positive charge is z minus a, and that from the negative charge is z plus a. So the value over here on solving can be obtained as kq z plus a minus z plus a upon z square minus a square, and the value is obtained as twice of qa upon 4 pi epsilon naught z square minus a square. Now the value of dipole moment for this dipole can be written as charge into separation between the charge. So 2qa can be written as dipole moment P, and hence the value is written as P upon 4 pi epsilon naught of z square minus a square. So this is going to be the answer for the first part, where it is asking us to calculate electrostatic potential at the point 0, 0, z, and for the xy plane the value of potential is 0. So this one is the first part answer that we have obtained. Now in the second part it is asking us to obtain the dependence of potential on the distance r of the point from the origin where r by a is greater than 0. So over here I am modifying this equation which we have obtained in terms of r, or the position vector. So we can write this expression as that the potential can be written as P upon 4 pi epsilon naught r square 1 minus a square upon r square. So if we consider this equation, so now over here the question is saying that r by a is greater than 0, greater than 1. So I can say that a by r is less than 1, and hence 1 minus anything which is a very small quantity will be 1. So the value of potential is obtained as P upon 4 pi epsilon naught r square. So V is inversely proportional to r square. So we have obtained this dependence on potential, that is inversely proportional to r square, which was needed in the B part. Now in the C part the question is asking how much work is done in moving a small test charge from the point 5, 0, 0 to minus 7, 0, 0. So as the particle is taken on the x-axis, the value of potential at both these points is going to be same, since the positive and negative charge is at the same separation at both these points, and hence there is no change in potential energy due to the motion of the small test charge, and hence the work done is going to be 0. So in the C part the work done is going to be 0 in displacing the small test charge from the point 5, 0, 0 to minus 7, 0, 0 along the x-axis. So obviously the answer will change if the particle is taken in any other plane apart from the xy plane. So the value of potential energy change will come in and hence the work done can be calculated by calculating the change in potential energy for the system. So now post this we are going to discuss about the equipotential surface and conductors. So we are going to discuss about the equipotential surface now. So let us begin with the definition of equipotential surface. So we say for a given charge distribution, the locus of all the points on the region for which the electric potential has a constant value on that particular place or the surface is regarded as equipotential region. Now such equipotentials can be surfaces, volumes or lines, and they are what is regarded as equipotential surface. So I am repeating one more time. For a given charge distribution, the locus of all the points or the regions for which the electric potential has a constant value are called as equipotential region. Now since such equipotentials can be surfaces, volumes or lines, we regard it as equipotential surface. So now what are the things that must be noted about these surfaces is, the first thing is the lines of forces always intersect, the lines of forces or the electrostatic field lines always intersect the equipotential surface perpendicularly. The equipotential surface perpendicularly. The next one is, no two equipotential surfaces can intersect each other. No two equipotential surfaces can intersect each other, because if they do so, they will have two values of electric potential at the point of intersection, which is simply not possible. Now the next thing which we say is, a charged conductor of any shape is an equipotential surface. A charged conductor of any shape is an equipotential surface. And the next part is, equipotential surfaces are crowded together in a region of a strong field, whereas they are relatively far apart where the field is weak. So the next point is equipotential surfaces. So this is equipotential surfaces are crowded together in a region of a strong field, whereas they are relatively far apart where the field is weak. Now the next thing is, if the charge particle is moved on an equipotential surface, the work done will be zero. So on moving a charge on an equipotential surface, on an equipotential surface, the work done is zero, and it is because there is no change in potential. We can also calculate work done as change in potential multiplied by the charge, and since there is no change in potential, we say that work done in such cases is zero. So these are the few points which must be first of all taken care of when we say that the surface is equipotential in nature. We can also understand these points or prove these points mathematically using this equation which we have already learned, that is v2 minus v1 is equal to negative integral of E dot dr. So while teaching this equation, I already mentioned the points which I have written over here. So if I say that the value is equipotential, so the equipotential implies that V2 is equal to V1, and hence we say that V2 minus V1 is equal to 0. So if the LHS portion is 0, so in order to make the integration of E dot dr as 0, so it is important that E vector is perpendicular to dr, and that was the reason why we were saying that the electric field lines intersect an equipotential surfaces perpendicularly. So this was the reason why we were saying that the lines of force always intersect the equipotential surfaces perpendicularly. So this was the reason behind this. So now we will be studying about the conductor in details, and we will be finding out as to how the surface of the conductor is an equipotential when it is placed in an electric field, and what are the other properties associated with the conductor. So now we are studying electrostatics of conductors. So whenever we refer something as a conductor, we mean to say that it contains a large number of free electrons. Now since there are a large number of free electrons or large number of mobile charge carriers, so what is going to happen is they will nullify the effect of any electrostatic field which is generated around it. So in case of a metallic or a solid conductor, we say that these large mobile carriers are electrons, and in case of electrolyte or a liquid conductor, we say that these charge carriers are in the form of ions. So it is not necessary that always the conductor is associated with large number of free electrons. They can also be considered as a large number of free ions. So now let us consider something like this. So I am drawing a conductor. So we are considering a conductor like this, which is a solid conductor, which is placed in an externally applied electric field. So this is externally applied uniform electric field that is present in space. So now the moment a conductor is placed in an externally applied electric field E, so I am calling this as E naught, this is externally applied electric field. So this basically implies that there is a large positive charge on the left hand side and a large negative charge on the right hand side, as a result of which the electric field lines is going from the left side to the right side, something like this. So we are saying that there is a positive charge over here and there is a negative charge over here, as a result of which an external field is created, and we have placed our conductor somewhere in between it. So as a result of which the negative charges is induced on the surface of the conductor, like this on the left hand face of the conductor, and a positive charge on the right hand face of the conductor. So as a result of these induced charges, the electric field is induced inside the conductor in the opposite way. So this is going to be the direction of the induced electric field due to the induced charges in the conductor. So now this induced electric field, which I refer it as EI, will nullify the effect of E naught, and as a result of which the electric field inside the conductor will become zero. So I can redraw this conductor like this, that the electric field inside the conductor is nullified. So there is no electric field inside the conductor, and it is looking somewhat like this. The value of externally applied electric field is E naught. So it is something like this. So we say E inside the conductor is 0. So now we say that over here, since E inside the conductor is 0, so if I apply Gauss law, so applying Gauss law, we say that cyclic integral of E dot A is equal to Q enclosed by epsilon naught, and from here we obtain that the charges enclosed inside the conductor will also be equal to 0. So there is no net charge enclosed inside the conductor. So this is the next deduction which we can draw, that there is no net charge inside the conductor. Now if we use this expression, that since the electric field inside the conductor is 0, and if we use this expression, that is VA minus VB is equal to negative integral of E dot dr. So from here, if E is 0, so I can say that VA minus VB is equal to 0, or VA equal to VB. That is, I can say that the surface of the conductor is equipotential. The surface of the conductor is equipotential. And if the surface of the conductor is equipotential, so I can say that the electric field is perpendicular to the equipotential surface, and hence on the conductor these external electric field are making an angle of 90 degree, or they are normal to the surface of the conductor. So this is how we say or we talk about a conductor. So we have deduced the following conclusions about a conductor: that inside the conductor electrostatic field is 0, and then we say that if we apply Gauss law, we find out that there is no net charge enclosed inside the surface of the conductor. The next thing is the surface of the conductor is equipotential. Now over here, I would like to take a very interesting note. Suppose we draw a cavity inside the conductor. So drawing a cavity inside the conductor, so if we consider a spherical shaped conductor, something like this, and if I place a charge Q in the cavity inside the conductor, so this is the material of the conductor. So now how is it going to affect, or how are we going to understand this? So now due to the charge which is placed inside the conductor, a negative charge is induced on the inner surface of the conductor, and a positive charge is induced on the outer surface of the conductor, such that the positive charge that is induced on the outer surface of the conductor is equal to plus Q, and the negative charge induced on the surface of the conductor is equal to minus Q. So if we consider a Gaussian surface somewhere over here, so we will say that the charge enclosed inside this Gaussian surface is again 0, that is Q which was kept and the minus Q which was induced, so the value is 0. and hence if we calculate electric field on the conductor, on the body of the conductor, so the value is again 0. Although the electric field is generated inside the cavity, so inside the cavity some electric field will surely be generated, but on the conductor the electric field is going to be 0, and we are seeing that all the charges which is even inside the cavity of the conductor has come on the surface of the conductor, and the net charge enclosed inside the conductor is 0. It is equally notable that the potential at this point, so if we consider that this point is at a distance a and this point is at a distance b, that is the shell is having an inner radius a and outer radius b. So now the region which is over here is equipotential surface of the conductor. So the region which is between VA and VB is equipotential. So now due to all these properties of the conductor, we say that the conductor is also finding an application in electrostatic shielding. So when I say that the conductor is finding application in electrostatic shielding, I mean to say that we can keep electrical instruments which are very sensitive inside a conductor, and they will not be affected due to the external electric field which is created due to any other external source around it, and the device will be very safe inside a conductor. So this phenomena is regarded as electrostatic shielding.